This is video 804 in our chapter on impulse, momentum, and conservation of momentum. So we're finally ready to start talking about conservation of momentum. And there's things that you need, some kind of standards that you need to know. The first is that in a closed system, momentum is conserved. In a closed system, momentum is conserved. So in a closed system, momentum is conserved. And because of this, defining your system is always going to be very important. So define your system first, usually with a diagram. And in the last video, we talked about how you draw boxes around and you determine if there's an external force there. The next kind of defining standard that we want to say is that you'll have interaction, but even so, but your initial momentum will always equal your final momentum. So even if you start off and the two objects are moving independently and then they collide and stick together, you'll still see that the initial momentum, and this is going to be pre-collision and post-collision. We're going to start talking about collisions here in the next video. The momentum in will equal the momentum out. Third thing, I'm going to write this in red because this is important. This is what trips up every student that has trouble with this chapter. Every student that I've ever had that has trouble, it's this. It's signs. I'm going to write that 3 times. I'm going to underline it. Exclamation mark, exclamation mark. This is why I think this is such an issue. In the last chapter on work energy was scalar, and we got out of the habit of looking at our values as vectors. Also, all the vectors that we handled in projectile motion and in force were usually going in opposite directions. Here we're defining systems, and so our vectors are usually parallel and anti-parallel, and so we kind of forget that those have signs too. You have to ascribe your signs or it doesn't work at all. And we saw that back with the first video, and we looked at the momentum change when we went from, when the ball came in, the ball was coming down, and that was a negative, and then it went up. When you add them together, instead of having -4 and +4, you end up with, because you subtract, you get the opposite, you end up with 8. So having the right signage is so important in this chapter. I cannot emphasize that enough. So let's look at a couple of sample problems to kind of figure this out. First thing you're going to want to do is to define a coordinate system. So let's say to the right is positive. We have 2 4-kilogram ducks and a 7.6-kilogram goose traveling towards a piece of bread in the water. The ducks approach from the right at 1.1 meters per second and the goose from the left at 1.3 meters per second. Find the total momentum of the system. So here we go. I'm going to draw a bigger vector because this is going to be 1.3 meters per second. And we have a 7.6-kilogram goose. And then over here, I'm going to have 2 4-kilogram ducks, and they're each going to have a velocity, and I'm going to make this a little shorter, of 1.1 meters per second. And they weigh 4 kilograms. Why don't you pause the video and see if you can work this out without the answer? Okay, did you take a crack at it? Well, the first thing you should see is if this direction is positive, these are going to have negative values for that velocity. So when I multiply this together, I'm going to get positive. Remember, momentum is mass times velocity. It's going to be positive 9.88 plus, I'm going to have negative 4.4, negative 4.4. When I add that up, I end up with a total net momentum of positive 1.08 meters per second. So what I did here was I found the momentum of the system. And you do that by taking, by the way, what I should have done, and I didn't, My black marker just decided to die. See if I can find a different one. And using good practice was to find my system. So what I did here, this is my system. So all of these forces are contained inside of this system. It's a closed system. Momentum would be conserved. Now, we're not actually even looking at conservation momentum here because nothing happened where momentum was going to be conserved. I was just in this problem analyzing what the total momentum is for my system. So for the next problem, let's look at an example where we actually would have to consider whether or not our momentum is conserved. Slide my camera. We're going to calculate the recoil velocity of a 5-kilogram rifle that shoots a 0.02 kilogram bullet at a speed of 620 meters per second. So the first thing I want to do is draw my diagram. And let's go with purple. I haven't used purple yet. It seems a little wrong to have a purple shotgun here, but bullet. That, and I'm going to be shooting the bullet. I saw the trigger come up there. Okay. So my system includes the bullet and the rifle, and we're going to make to the right positive. So what we have happening is we have a force of, call this R and B. So we have the force, let's do a free body diagram, on the bullet by the rifle, and we have an equal and opposite force on the rifle by the bullet. So we know that by Newton's third law, we have two forces going on here, and they're going to be equal and opposite. It's an action-reaction pair. But we have different masses. This is 5 kilograms. And the bullet is 0.02 kilograms. So let's use conservation of momentum to see if we can figure out the velocity of this gun. We know that the initial momentum is going to equal the final momentum, or you could say the momentum of the rifle of this force is going to equal the momentum exerted by that force. So this is going to be mass of the rifle times the velocity of the rifle. This is going to be the mass of the bullet times the velocity of the bullet. You can do variable banks here. So in this case, it's simple enough that I'm just going to plug in my values. And the other thing is make sure everything's in kilograms. So this is going to give me 5. And we want to calculate for that recoil velocity. It's going to be equal and opposite to 0.02. And it says this velocity is 620 meters per second. When I solve for the velocity of the rifle, I get that I have 2.5 meters per second. The other thing that you could do is you could say that you could take mass of the rifle times the velocity of the rifle minus the mass of the bullet times the velocity of the bullet as equal to 0. That's doing the same thing basically. And what we see here then, this has a negative term, which makes sense with our coordinate system. This bullet, the forces that are exerted there are going to be negative. So we're going to have a negative velocity. I'm sorry, a momentum. The momentum would also be negative, which we see there, and we would get the same answer. Okay, so let's start off with some, the homework assignment for this has some kind of basic conservation momentum problems. Again, what we haven't done yet is we haven't considered collisions. That's in the next video. And we're going to look at the 2 categories of collisions that we can have, and we'll see how momentum is conserved in those collisions for closed systems. Okay, that's all for now.